Yeah, I think we can start. Let's start with Nathan and then go up from there.
Okay. I'm not sure I can quite see the. Oh, I can see. Um. So yeah, I don't know. I'm not sure I have a lot to say. I found the discussion of the execution layer a lot more straightforward than the consensus layer, and I think that's because um, a lot of this is just really just normal virtual machine stuff. Not in the sense of like hardware virtual machine, obviously, but like Java virtual in the sense of like Java virtual machine. Um, and there's obviously a lot going on around verifying blocks and whatnot. But like the mechanics of the EVM and the idea that it's like, okay, so we've got to, really all computers are state machines. And it's like, okay, so we've got a virtual machine and we've got a current state and we need to, calculate by some set of rules the next state. And there are many possible next states, obviously. But we have like certain things that we can use to get that next state. We've got this pool of transactions to draw from, and which of those are going to let us get to a particular state. And there's rules around that, around, can I actually run this transaction at all? Is there enough gas to run it? But then also questions about like, you know, how do I order the in order to kind of maximize what I'm getting out of it. And then that's kind of where you start getting the interaction with the consensus layer when you're handing that back that we're talking about. But like the actual mechanics of it, it felt a lot more straightforward to me. I mean, I think there's some really interesting stuff like the gossiping to square root of n peers, and then you just are checking or full transactions, and otherwise you're just checking hashes. That's like really clever and pretty cool. I think the biggest thing that I had a little bit of trouble, and I think maybe still getting my head around is the the need the healing step that needs to happen during the snap sync. And I think like I've been thinking that through, and I think the reason that's there why you can't just use the block is it's not so much about um, like knowing my current state because I should know that current state from the current block, but it's about verifying that state. Because I'm missing now that sort of some of those potentially intermediate edges in the vertical tree that I would normally walk up to verify, uh, particular states. And so I think that healing stage is actually necessary for the verification of the block, and not because I needed to be able to calculate the next step, assuming the block is valid. Um, so I think those were sort of the takeaways for me. That you know, in a weird way, while this is where the magic happens for a lot of a lot of people, or I think at least what I'm interested in. Maybe other people are not, but the sort of world computer aspect is kind of the magic. But it's also like almost the more vanilla part of things, which is probably good overall. There. So those were my thoughts. I mean, obviously, some of the details in there are also interesting. The fact that everything's 256 bit because because that happens to be what we can fit a hash in is pretty fun. Um, I think the other thing I'll just say, and then I'll pass up, that did stand out to me is I thought that gas prices per transaction were that there was actually more to it rather than it being kind of like, well, we just benchmarked a bunch of this, and then we've kind of been just putting things around ever since. I thought that I naively thought that there was there was more to it about both in benchmarking and maybe that it was set a little bit more dynamically. So I was a little bit surprised about that, and it does make me think. I think like Client had some comment in the lecture about like things might actually be overpriced, and I would be kind of curious if there's a way to dynamically recalculate these things or something to get more realistic gas prices. So those were my thoughts and the things that stood out to me, and I will pass up to Ben.
Hey, yeah. I'm not a master of Ethereum, but I do know I've definitely seen execution stuff before. One thing a perspective I want to try to bring into this is to talk a bit about like the history of where this comes from. So way back in the day, Bitcoin. I don't want to go through all the details of the Bitcoin system. It's complicated if you're not or haven't already been, aren't used to or exposed to it. Um, but basically, let's talk just about the Bitcoin execution layer, which is really just UTXO scripting, which in the very early days was like one object. It was like you put the signature here. That's why it's called the script pub key, public key and signature, and then that's it. It's like it's almost not even a script. It's just like a place to store a thing. That was like early Bitcoin days. That's what Satoshi put there. But being Satoshi, he did a lot of stuff that was pretty forward thinking, and said, all right, let's have a scripting language here. Bitcoin script, the original Bitcoin script, had a bunch of cool stuff in it that immediately broke and was all basically banned. So, and if you don't know the history of Bitcoin, you might not know this. Bitcoin script had all these cool opcodes and it was very buggy, and like you could set up scripts that were like completely busted. And very quickly they basically soft forked out all of the scripts beyond just very basic multi-sig and basic spending basically. Um, and so all those scripts actually still exist. They're all still currently banned. If you observe the Bitcoin ecosystem at all, you see people talking about like opcat, or like opcat was an original script that was originally banned, and they're talking about unbanning it. And I'm getting a bit off the Ethereum chain, but I think that's important history. So Bitcoin scripts are all localized into a particular output, which is you can think about Bitcoin scripts being attached to a particular instance of a coin. Now, Ethereum is, of course, designed to be much more general. It's fully Turing complete, can modulo the fact that, the execution is limited by gas. Whereas Bitcoin, everything is sort of localized. The Bitcoin system is necessarily local to whatever current version of the UTXO you're working with. Whereas Ethereum, there's generalized storage that anyone can access. So you can, put rules down and sort of run as the original idea was a world computer. So you have this sort of generalized EVM. Now EVM, when it was created, it was sort of just thrown together. They did have a yellow paper, I think they called it. But if you actually like look at the EVM, I don't actually think it's that great made. If you that great made. If you like there have been a lot of attempts to rewrite it over the years. I think Fuel, I believe, was a rewrite of the EVM. Some other historical stuff whose name I'm currently not remembering, but you can certainly look it up. Like I think Optimism and a lot of the roll-ups that took the EVM and are like, how can we do this properly now that it's been half a decade and we sort of have a better idea of what we're doing? And try to change it to be a better behaved object. But at the end of the day, if Bitcoin scripts are these extremely localized things, EVM is just almost a general like CPU, except it's not really a CPU, and you have the weird stuff like the 256-bit words, which if you actually look into how you actually implement on a real CPU, it seems insane. Like, why would you do that? And it's like, oh, because it means hashes can very easily fit, and aren't hashes really important to blockchains? And yes, and yes, and yes, but that was still dumb. um, but yeah, so and I think, and this is where I'm pushing my boundaries, but I think Solana has something that's EVM like, but not quite. A lot of the new stuff is either EVM compatible or sort of EVM compatible, like with some of the edges sanded off. And then and yeah, I do like how Nathan was like, I thought there was some kind of complicated calculation for gas, but no, like the basic gas prices for various opcodes, that is pretty much just done, and it sort of has to be done just in terms of, all right, we ran this opcode a bunch, and this is sort of like the best and worst case, so we'll eyeball it. There is no sort of theoretical way you could figure out like what the gas should be, because it's fundamentally dependent on architecture. And this is sort of goes back to the old this arguments about gas prices. You can look at the history; it flows all the way back to like 2017. There was a lot of arguments in Bitcoin about block size limit. Bitcoin doesn't have gas prices. You just look at the bytes of the transaction because there's no loops. So that's a rough approximation of how hard the transaction is to actually verify. Um, Whereas because Ethereum has loops, you could fit in arbitrary amounts of verification into tiny bits of code with just do while true. Um, so that's why you have to break it down into smaller pieces. There's been arguments for splitting gas even further down to like storage gas and processing gas or so. Um, if you could exactly compute gas by counting opcodes. I'm not sure if it quite get you to like being solving halting problem hard. But I wouldn't be surprised if something like that was the case. Because, it just comes down to like, so, the Bitcoin block size, it's set to a megabyte. What is a megabyte? It's a million bytes. But what does that mean? Like, you have to know, all right, I have a hard drive that stores, 3 terabytes or whatever. And that's sort of in that sort of theoretical sense, that's totally arbitrary. Why don't I have a crystal drive that stores, exabytes on my desktop? And that's just because we have the technology to make a hard disk that stores terabytes and not exabytes. So if you imagine that there's no sort of fundamental limit, we're so far from the actual fundamental limits. You could imagine a hyper technological race having, 1,000 times or 1,000,000 times the bandwidth capacity, to which like, terabyte block size is like, oh yeah, that can totally be done on a phone sized object. And in that case, you could argue that yeah, the Bitcoin block size should be terabytes, but you have to link it to like what people actually use. Um, Now you could imagine in Ethereum it would be some kind of process to actually set this number. Like maybe a committee would go out and test opcodes or test transactions or test state updates against various sets of test machines, and being like, all right, we have some like systematic institutional method to calculate these. But Ethereum didn't quite go down that route, and there are historical reasons for that. But mostly because it was sort of slapped together at the beginning. Um, and the EF doesn't want to end up being that sort of kind of standards institution. But you could imagine it being done that way. Um, all right, I think I feel like I've blabbled on for like 10 minutes, so I will pass it to Anraj.
Uh, yeah, so I quickly went through the technical part, but like uh, basically it does the runs the EVM and this execution layer. I find it quite interesting, primarily because for my day job, what I do is basically bring up silicon CPUs. I don't write the RTL for it, but I do help the hardware engineers to bring it up. So the architecture of the EVM, like I find it fascinating because most of the virtual machines are like stack-based machines, and in the real CPUs, nobody, at least after the 80s, nobody builds. Register stack-based machines. So most of the CPUs you see are register-based machines. So that was an interesting like thing that stood out to me, like, and how they have built the EVM. And so these are, and I think there are some efforts to do some RISC-V based EVMs, or like at least on the ZK zero knowledge world, and people are trying to build some ZK VMs based on RISC-V. I don't know exactly how that works. So that is also what I have found to be interesting. And like, so basically, like if I'm going to some Ethereum conference, like I try to go around what the EVM people are doing. And recently I found out about something called a nerd miner. It's like a pooled mining uh, protocol. It runs something on something called the Stratum protocol, and then it basically allows small microcontrollers to participate in mining. And yeah, so like I just bought a small microcontroller to run it. I've not run it yet, but yeah, probably I'll be trying that in the coming weeks. And I've not seen something similar for Ethereum yet, but I think it is possible to run some sort of clients on microcontrollers. And with that, I'll pass it on to Venkat.
Yeah, this is my understanding of all this stuff is limited. So shallow scan, it seems to hang together, and um, I guess the couple of points that stood out to me relative to other distributed systems you might compare to is again client diversity being a super important thing for actually delivering the properties claimed. There are lots of other blockchains, they kind of don't recognize how important client diversity is, so they have particular fragilities. That's one, I think, distinguishing feature. The other distinguishing feature, I think, is since history becomes so huge, you kind of do need the spectrum of nodes from light to full and archival, and make pragmatic choices about how much of the history you're going to store, how much of it you're going to like actually validate versus trust based on receipts. That entire stuff seems to me a whole interesting architectural domain because it goes to like I think what's becoming increasingly the core of computing, not just blockchains but AI as well, where the bottleneck is increasingly memory and memory bandwidth, so and storage costs. So architecture starts to be driven by how you handle memory in one sense or the other. So this is, I guess, one extreme. And I know there's been a lot of conversations about in the future making the execution layer entirely stateless. So I'm not quite sure how that would work, but that means, I guess, that all historical data would be handled some other way, like offline with some sort of like cryptographic verification of stuff. A couple of other things I wanted to flag that I've heard a lot of conversation about that you guys may want to like comment on or think about is one is there's been a long running debate over the self-destruct opcode in the execution layer. Like everybody wants it gone, but there's a lot of legacy contract code that depends on it. But self-destruct basically allows you to kind of like wipe away the data of and state of a contract and kind of transfer its balance to a new wallet or contract, something like that. So it's kind of a way of uh, basically writing off accumulating, I guess, not just technical debt, but execution debt and in the world computer. So it's kind of like I don't know quite how to think of it. It's like some mix of like garbage collection and refactoring going on live. So it's interesting to think about because it's been so long a topic of controversy and it's kind of deprecated now. But I think they still haven't managed to remove it from the definition. So that's one of the things I think that's interesting to think about. The other is I've heard a lot of discussion lately in the last couple of years about the Ethereum object format. So they kind of want an object format to run on the EVM, but there's like endless discussion of how big it should be and how it should be implemented. So it's kind of been stuck in um, the ACD limbo for a couple of years. So those seem to me interesting about the ways in which they want Ethereum to evolve. And I think the takeaway from that is there's like ongoing debate on like how complex the EVM and low-level software running on it should get. Um, yeah, that's it. Passing up to Sachin.
Sachin is in listen mode. Uh, Maybe if Jenna wants to chime in. about something.
I think Venkat mentioned stateless execution. And I do want to talk a bit about that because that's sort of a cool thing. It's not directly related to the execution layer in that it's sort of like an implementation detail. Let me try to explain it. So if you imagine sort of a basic program, you have some state, like you have, say, a variable, it's like 1, and you want to add 1 to it, and you know the answer is 2. And you can either sort of have the 1, see that the transaction is adding 1, and then say, all right, output is 2. We know that's verified because 1 plus 1 is 2. The stateless execution is you don't have any of the numbers, but you get a transaction that says, I am adding +1 to this thing, and I have a proof that this thing is currently 1. And then you say, yes, we know it's 1, not because I have the data, but because this is a proof that it's 1. And the transaction adds 1, and 1 plus 1 is 2. Proof verifies. Transaction is valid. So basically, the idea being that nodes, in the sort of the person who has to hold the state goes from sort of like the node operator who holds everyone's state, to the person who actually cares about the state has to hold on to that state. And then when they want to interact with that state, they have to prove that the state is correct. So instead of the nodes having a list of all the numbers and then being like, all right, I'm taking this 1 and adding 1, it's the node doesn't know anything except you give it a proof that, yes, the current value of this at here is 1, and I'm adding 1 to it. And as you can see, 1 plus 1 is 2. So that's just sort of, it sort of like inverts the actual structure. It's interesting. I'm not sure how well it would actually work in practice because people are not used to having to carry around their own state. And you have to prove everything, which means that um, if that's expensive, then it doesn't actually save you much of anything if you're spending all your time creating and verifying proofs that the state is what it is, as opposed to just having the state. But Ethereum state is nasty in that it's old and it's accumulated a bunch of stuff that no one cares about anymore from like ancient projects from a decade ago. Um, so the idea being that if everyone went to switch to stateless mode, the things that everyone used, everyone would have because everyone's using it. Whereas the old stuff that no one cares about anymore would get lost and forgotten, and no one would ever care about it again. And it'd be a way to dispose of the old stuff without actually having to technically remove it from the state. Because if someone kept a proof of its existence, they could come decades later and be like, I have this ancient proof I found in this cave that proves I can take all this money, and the nodes be like, yeah, sure, proof is valid, you can have it. So yeah, that's the stateless. I'm not sure if that was actually a good use of time, but I do think stateless execution is interesting. So yeah, there's an explanation.
More thoughts? Uh,
It's worth, I think, watching a couple of ACD calls just to get a sense of how people um, talk about managing the evolution of execution layer. Like consensus layer was kind of like a briefer period. It has a shorter history and it sort of needs less touching, I guess. But execution layer is like always an entertaining circus debate that's just going on and on. So worth watching a couple.
more thoughts? Okay, if not, then we meet again in 2 weeks. Bye.